Hi, my name is Vernon Mauery, and today we're going to be talking about the trusted execution environment on the OpenBMC platform. I'm a firmware engineer at Intel, working on the Intel server platforms, and my areas of expertise are in the security and bootloader area. So um, I this is one of the areas that I thought was important for OpenBMC to have. So this is one of the things that I've been trying to push forward on our team.
Hi, my name is Zhikui, and I'm a firmware engineer working at Intel on the OpenBMC project. I've been working for the embedded firmware for a while, so but I'm relatively new to the OpenBMC.
To start with, why would we really want to have a trusted execution environment? Well, the objective here is to be able to keep a secret. Keeping secrets is a pretty difficult thing to do in general. It's the hardest part of crypto and security, because once you've done that, you can do a lot of other things. So we're going to talk today about how we can keep a secret, and then some of the things that we can do, and the first steps that we've taken so far. So the very first thing, we need to be able to trust yourself. So the slide says know thyself, but really it's trust thyself. And how do you do that? Well, you start with secure boot. So applications running on a Linux kernel could be in a signed file system or authenticated at load time by the kernel, but still they're only trusted as far as the kernel is concerned. So the kernel, when it's loaded, could also be signed and authenticated by the bootloader, but then the bootloader needs to be signed and authenticated. So it's kind of like turtles all the way down, this chain of trust. And chains of trust are really only as good as the weakest link. So we want to be able to make sure that there is a point of trust, a root of trust at the beginning here. So on the ARM platform that we're working with is the AST 2600, but it's obviously not the only BMC, but the same sort of architecture could work on a variety of things, since the mechanism that it uses is, well, the main mechanism is common to a lot of ARM processors, and a lot of the SoCs have the extra features needed in order to be able to implement this. So on the AST 2600, the first thing that happens is the SoC starts executing this ROM code. And so the ROM code is, in theory, more trustworthy because, one, it's immutable, two, it's generally a small chunk of code, and three, it runs early enough that it's hard to get anything in to attack it or to change it at the time that it's executing, when it's coming out of reset. So the SoC boots up this ROM thing, which then knows how to load a small chunk of code from the SPI flash or from the eMMC, and loads that into the internal SRAM, where it can use the one-time programmable keys that have been provisioned already, as well as the hardware crypto engine, to be able to authenticate a signature on that code. And once it's authenticated the code that's in SRAM, it allows execution of that code to begin. So that's the root of trust, very first thing that executes. once and in the OpenBMC situation, the first code that's going to run is this uboot SPL, which stands for the secondary program loader. Secondary because the first thing that is running is the ROM code. So this SPL, it has a very limited scope. It basically needs to initialize the DDR in order to load a larger image and do some very basic hardware initialization in order to be able to execute its code and load this other code and authenticate it. So it's going to load this larger image, the full uboot image, into DDR, do authentication, probably or possibly using the crypto engine, but not necessarily. It could use software crypto routines, but then it authenticates the uboot and jumps to that. And uboot then has a built-in way to authenticate the fit images that it loads and executes. So those are also authenticated on the way up. So we can get secure boot, but that's still insufficient to really trust everything. And part of that's because the further you are from this root of trust, and when I say farther, I mean in time mostly. The farther you are in time from this root of trust, the harder it is to know that you're still trustworthy. So by the time we get to, SPL, uboot, kernel, runtime, applications are executing, a lot of stuff could happen. You've got interfaces that have come up and other opportunities for bad actors to come in and break things. So we would really like a way to kind of know something is more trustworthy somehow. And it's kind of like time travel in my head. The way that we're doing this is we're going to, early on in the boot, split the hardware into a secure and a non-secure world. And the non-secure world boots up normally using the secure boot mechanism, but the secure world boots up a very small core and only gets used in certain situations where security things need to happen. So then whenever you need to use a key or sign something or decrypt something, the non-secure world can make a request to the secure world and kind of travel back in time to a place where we're more trusted. In order to do this, though, it requires some hardware augmentation, and ARM does this with what they call trust zone, which at the root of it is basically a extra bit in all the page table entries and some extra registers in order to kind of like a hypervisor split the CPU into secure and non-secure. And so anything in the secure world can access all of the stuff, secure or non-secure, but anything in the non-secure world can only access non-secure things. So part of the consideration, though, is we need to be able to start this world, this secure world, as early as possible. So if we'd waited until Linux is booted and we started to launch it, then that might be considered too late because we might have already executed some flaw in the Linux kernel. So if we can start it earlier, like very early in uboot, then that would be ideal. It's possible to start it before uboot, but that would require even more work to port the secure monitor to to the platform in order to execute it first. So next we're going to have Zhikui talk more about what we've started to do with the trusted execution environment once we've got it up and running.
So we have done some, thank you, Vernon. And I'm just going to talk about what kind of proof of concept work we have done, trying to introduce a trusted execution environment in OpenBMC and using that to keep a secret, basically. The first thing we did was porting the OptiOS onto the ASPEED 2600 chip, and that one has the support for trust zone extensions. Then we picked our first target, the secret we want to put it in the secure world, keep it safe, is the IPMI password. And we modify the normal world application to leverage that new trusted application. So I'm going to go into details about each of the steps. This obviously was, sorry, I'll get too far. Should talk about this as the first step is the porting portion to make Opti run on our this new chip. ASPEED 2600 is a BMC chip. So basically, there is a good guideline to go off from the Opti's documentation website. And here I listed the files we have to modify to make it run on the silicon we have. And so very briefly, the conf.make file was just configure what features we pick from the Opti. We stayed with the basic functions and leave out some of the advanced functions we don't need right away. Main.c is where we just customize how the interrupt controller and UART get initialized. So platform config.h is where we specify the memory map and how we reserve the memories for the trusted applications and Opti itself, obviously. And then there's some work to support the second core. It's to boot up in this, be able to manage the two world, as the secure world and the normal world, as we say. That's the first thing. Once we get it compiled and running, like Vernon mentioned, we trying to see how it fits in. We want it to be as early as possible, but we just need, in the interest of to minimize the work and get it up and running quickly, we basically keep the U-boot portion and have U-boot load the Opti. And then once the Opti initialize the secure world, all the hardware and reserve the memory for that, then it loads to your normal Linux kernel, and then it goes on to load the user applications. The way we accomplish this is through the fit image specification here. As you can see, the Opti is added as a module specified. It's a kernel type, and where it's get loaded and where is the start address is. And we just add a configuration to use the Opti module as the kernel and make the kernel as a loadable after that. So that worked out really nice. We can switch and back and forth to run normal as before without Opti, or has Opti in the middle, and test out new software that way. So very quickly about IPMI user password, how it's used today in the OpenBMC This is a user management documentation from the OpenBMC GitHub. And here is the thing we're talking about is mainly about how the IPMI password is managed. Today, it's saved in the file system encrypted. It used through the, so it is used in the RACP protocol specified as part of the IPMI specification. And the code, the service to support the IPMI, load the file and decrypt it, and the user password is cached in memory. So it can be ready to do the session negotiation with remote. So that's also, I want to show how the building blocks for the T framework we're talking about here. Linux kernel has a subsystem to support the trusted execution environment. And those drivers helps to communicate from the normal world into the secure world. And this side is what Opti provides. So it has its own OS and execution under the secure mode bit set, as Vernon mentioned before. So that's in the trust zone of the chip. So the two things we used for our proof of concept work is this dynamic trust application. It runs in the user space, but it's in the context of the secure world. And the secure storage, there's a trusted storage API it implements and often used to manage the key, the secrets. It has its own protocols to encrypt the files, and it can only be decrypted and read with trusted application in the secure world. There's no access from your rich, we often also call it rich execution environment, which is a normal world, another way to say it. So those are the building blocks, and those are what we're using to trying to go back to our go to secure a secret for our OPM, the IPMI usage here. So we basically, the two main goals, right, is to store the IPMI password in the secure world and remove all the copies and needs to hold that in the memory in the normal world execution. So here's the program flow as today. It's basically there is a step you load and decipher the user keys, and then it used in generate the HMAC in the session negotiation and passing the user key as a parameter in that function. And we want to split that into this new scheme with secured, trusted execution environment. Basically, all the secrets we want to the user keys, the handling of that to keep it in the secure world, and the rest of negotiation can be done in the normal world. To look at a little more detail here is how this program flow works. This is the core function we're replacing, the generate HMAC key. Now you notice with this transformation, only username needs to be in the parameter and passed through. The first thing it does, it's called the prepare T session. With the support of the Linux kernel drivers, it will do it magic and actually find the trusted application in a secure world and load it So next, we'll call this function to generate the HMAC. So that's part of what IPMI, session negotiation steps defines. That's one of the things it needs. But again, here we only need to know the username, and then it's handed off to the secure world. This entry key here function, the HMAC SHA 256 does all the real work. It will try to find in the secure storage the user keys for that user, and then to do the computation of the HMAC value and then pass it back in to the normal world. Once that's done, we'll call a terminate key session, and that's going to unload the trusted application in the secure world. Similarly, how you set up a user and install your key initially, it's follow a similar flow. The real work and content is happening on the secure world, inside secure world. So the normal world is free of those secrets, don't have to keep those anymore. So what is next? The next is clean up these implementation, complete, and then also we want to explore the option like Vernon pointed out to even start Opti earlier. Here's a picture of the different options we were looking at and maybe experiment. But there's a lot more, and Vernon is going to talk about that.
All right, so what can we do once we have that initial secret and a safe, secure execution environment? Really, we can keep more secrets and do more secure stuff. So that initial secret that we're keeping is called, in the Trusted Opti lingo, it's called the hardware unique key. And that is the initial secret that we store. And that's what's protecting all of the other secrets that we have. So once we have that, then we could like store keys, create keys, and securely keep them in the world. Basically, a lot of the things that a hardware security module would do are an HSM. So if you've never used an HSM, they are pretty cool because they can do a lot of crypto things. Partly they can do it quickly because they're hardware accelerated, but also they can do it securely. So as a human, I can't just go poke into it and figure out, oh, well, here's the private key, or here's the secret key. It has an API that you have to use in order to access the keys, and it uses them on your behalf. And so we could basically create an onboard HSM in the secure world and have it do things like key creation and usage. So the web server could have an actual secure key, and then whenever it needed to use it, it could make requests to the to Opti. We could have it be a trusted time source. So time is often a factor in security. You need to know what time it is in order to like revoke keys and ensure that events happen in the right order and that sort of thing. So timestamping is an important thing that the Opti could do. It could also do random number generation in a secure manner. The kernel does a pretty good job at it. What if the kernel got hacked? Well, it's harder to hack the HSM or the secure world Opti because it's hardware partitioned off from the standard runtime. It's smaller, so there's not as much code to attack. So in general, the HSM there would be a pretty secure place to put stuff. And it's possible to write an OpenSSL engine wrapper to be able to access that. So you could write an OpenSSL engine that would, behind the scenes, open up these T sessions, do some operation, and return with the results. Kind of, and you would specify that instead of working on locally accessible files, you would give it some file handle essentially, and that would be the identifier that the Opti would use in order to open the real key and make use of that. So then you could just use your standard OpenSSL runtime stuff and just specify use the Opti engine, and it would be able to do that. General secure storage is another option that's already actually implemented as a secure application in Opti. So it would just be something that if you needed to do that, you would be able to. We could make it so that you had to have some user password in order to decrypt it or something like that to prevent different, or to do access control basically on the file. That way you could, not just anyone with access to the trusted execution environment could access it, but you have to have an additional secret to do that. Restrict critical hardware I/O access is a kind of a big one, and this requires even more hardware support than just what TrustZone does. The SOC that this is all baked into would need to make sure that it's properly adhering to the bits set up, so that if you mark a particular I/O region as trusted or secure, then it would have to really actually partition that off, so only the secure world could access it. But then you could do things like have a secure I2C bus, or have restricted access to your ADC, so you could, have trusted read of your voltages or whatever. It just offers a region, or a way to limit access to critical hardware that would make it so that you could have a safer system. And the last thing that we came up with was secure firmware updates. So the Opti world could perform like BMC updates on behalf of the rich execution environment, where the BMC would say, well, here's a new image, and the trusted world would be the final arbiter of whether or not it's accepted. So it would do the image authentication on the secure side, and then it could also possibly have restricted access to the flash, but that would be, restricted access to the flash would be a lot harder and a much heavier lift. But it would certainly be possible, assuming that we could restrict critical hardware I/O. So basically, once you have the secure world and you have a way to keep that initial secret, then really it's just a matter of whether or not you can imagine a way that you can split this work into the secure work and the work that can be done without trust. And the sky's the limit. So we do hope that we can get this into OpenBMC at some point in the future. It is kind of a big project, and we're hoping to have conversations with the rest of the OpenBMC community about what they would like to see in it. But we initially started with this idea because storing IPMI passwords is so insecure without a way to store a secret. And that's our presentation. So I guess next we open it up for questions later.